All right, let us start. So we're going to start a new unit in polynomial functions. So a polynomial function is a function in the form that has the form y is equal to a subscript n x to the power of n plus a n minus 1 times x minus 1 plus dot dot dot, and it follows this pattern. So really it should be, there's a typo there, by the way, I apologize. So really a n x to the power of n, a n minus 1, x to the power of 1, and then presumably so on and so forth, right? It follows the pattern in which we reduce the exponent n by 1, and we go all the way down to where the exponent is 1. And last but not least, this term even follows that pattern because x to the power 0 just really is 1. So it would be a naught x to the power 0. So it ends up being the same. So regardless, now I know that some of you guys are quite scared when you look at this. And I would be too, quite honest. That looks mean and nasty. However, you have a lot of experience dealing with polynomial functions. Much, much more than you realize. So there are some very special terms. So specifically, this first a n minus 1. Now, what are these a's? These a's are just simply constants. So, and generally a are integer values, right? So they're just the numbers in front of the, or they are the coefficients. The degree is known as, well, I guess a teenager would say the degree of a polynomial is the largest exponent. The number in front of the x would then be called the leading coefficient. So an is the leading coefficient. X to the power of n, well, n would be the degree of the function, and it's the largest one. And a naught is the constant of the function, and it is the y-intercept. You are quite familiar with this. So these seem unruly, but you have a lot of experience dealing with them. So I'm going to give you your first example of a polynomial. So we have you already know three cases. One is degree 0, and we call this the constant, a constant function. In other words, y is always equal to 0. This has degree 0. Now you may be asking yourself, why is it degree 0? Because if somebody was wishing to write it as an exponent, they could also write it as y is equal to 4, x to the power 0, where exponent is 0. Those two are the same. So you can graph this as just a horizontal line. We are more familiar, perhaps, with this. This is a linear function, right? It is degree 1. You may be asking yourself, why is it degree 1? Well, very simply, it is implied that the exponent above the x is 1. Now here, let's get back to our definition of a leading coefficient. Here my leading coefficient would be 2. So leading coefficient of 2, degree 1. So let's switch up colors, blue, why not? Variety is the spice of life. What you should be an expert on from last year is this type of monster. Now this type of monster is our good friend, the quadratic. So a quadratic function really is the progression of this polynomial. Now a quadratic function, if you notice that our degrees are going up by 1 each time, right? You are familiar with this. And incidentally, allow me to write down another quadratic. So here, y is equal to x squared. So this is still degree 2 because my highest exponent is 2. My leading coefficient here is 1. It is implied that there is an invisible 1 in front of that. Now, what is also interesting to note, now this can get really long. But really what we're saying is, I don't need this extra garbage here. Like, I don't need these extra terms. It's just y is equal to x squared. I don't need those extra terms to make it quadratic. Let's go on to the next one. I'm going to make this, oh, this is going to be beautiful. Look at that. That is to the power of 3. Now, we call this a cubic function. So this has a lot of terms in it, and what you can see is that it's getting very long. So this is called a cubic. Now, another example of a cubic could just look like this, right? Minus 4x cubed. It doesn't need to have all this other garbage. The y-intercept of this first one here really is -4, whereas the y-intercept of this one, well, would be 0. There's no constant term, and then we assume it to be 0. We can add more. Red's kind of getting boring, so I'm just going to switch up to blue. This would be a quartic, right? And now, how am I picking these numbers? I don't know, just for fun, right? If I'm trying to make up an example of a quartic, what's really important is that I have degree 4. My highest exponent is 4. Now I'm going to write one more. Now, I'm not expecting you to know how to graph this or this for now, but let us graph this. I'm just kidding. But this is kind of getting big and nasty and unruly. Sorry, that should be exponent 4 minus 3x to the power of 3 minus 7x to the power of 2 minus, this just keeps on going on and on, plus 7. So these, remember, now these individual parts, we call them the terms of a polynomial. Now, the numbers in front of each, sorry, that's bad highlighting, I'll pick yellow. The numbers in front, or I guess it would just be 7, right here, the numbers in front of all of the x's are known as the coefficient of each term. And very specifically, the coefficient in front of the largest degree term is called the leading coefficient. All right, that was a lot of fun. Maybe, perhaps, let's move on. Now, suppose, okay, here are some properties of polynomials. You do have experience with this. Now, here is my assuming statement. Here is a statement that I'm making. And whenever you see the word suppose, it's actually a really powerful word in math. And it is almost like, let us base a whole conversation around this assumption. So suppose the degree of a polynomial is n. It's the largest exponent. Then, perhaps I should add the word then. Then, the maximum number of turning points is n minus 1. The maximum number of zeros, or x-intercepts, will be n. If the function is an even degree, the left-hand and right-hand side behavior mimic those of other even degree functions. So think of quadratic. If the function is odd, the left-hand and right-hand side behavior will mimic those of odd degree functions. Now think linear. The y-intercept is located at a0, the constant. What? Like, I'm not expecting you to know this, but hopefully, throughout the unit, we'll have all of this, okay? It'll be, hopefully, let us do this table, and I'll try to do it right, okay? It's a lot of business that I just dropped on you, and I'm just going to draw my Cartesian plane for each of these. So I'm just going to draw it. I'm going to press pause. I pressed paused. I guess you guys didn't want to see me draw these Cartesian planes here, but this is just a sample. So right now, I'm just going to take some graphs. I'm going to take this, I'm going to select green, and I'm going to draw a constant function. What might a constant function look like? It is like this. Now, y is equal to a0. So for instance, I give the example y is equal to 4. It's just a constant function. Y will always have that. Allow me, now this is to demonstrate another function. There, this is another constant function. This might be y is equal to 2. So what the whole purpose of here is this is degree 0. That's what a degree 0 looks like. The maximum number of turning points really doesn't make any sense here, because if you use that formula where your degree is n, you'd have -1 turning points, and it doesn't really stick for this argument. Maximum number of zeros really doesn't stick for this argument as well. You have no zeros, right? But then as somebody pointed out, well, wouldn't you have an infinite amount of zeros? Okay, let's just ignore that. Anyways, now I'm going to switch colors. I'm going to graph a linear, and linear y is equal to mx plus b, by the way. So I've just made this up. There. That's what a first degree or a degree 1 equation looks like. Or alternatively, now I'm just making these up at random, but there, that's what a line looks like. Lines are degree 1. How many turning points are there? In turning points, really think of a vertex. That's what we mean, right? Like a little bump or something like that. Well, they'd have no turning points here. How many zeros do we have? Well, for the green graph, we have 1 0. For the blue graph, we have 1 0. Maximum number of zeros for a line, it has to actually cross the x-intercept. Now, a quadratic. I'm going to draw 3 examples of a quadratic. You are thinking of this quadratic. Yeah? So this is degree 2 for quadratic. Some of you guys are like, oh, no, I thought of this quadratic. Okay, good for you. Now I'm like, oh no, contraire. I'm going to draw one that is upward opening. It's interesting how I said upward opening. Anyways, what is common with all of quadratics? They have a maximum of 1 turning point. They have to have 1 turning point. And we spent much of last year talking about this turning point called the vertex. But what is the maximum number of zeros? Well, for a quadratic, you could have, if you look at the green, 0 zeros, no zeros. The red one is 1 0, and the blue is 2 zeros. So the maximum number of zeros that we can have is 2. Even though we could have 0 and 1, but the highest number of zeros we can hit is 2. All right. Now, I'm kind of hoping that, by the way, if you're like, how is he doing this? Well, it's through experience. I'm not expecting you to graph a cubic, but would it be a surprise to you that a cubic might look like this? Sort of like a quadratic, but then it bounces back up again. That would be an example of a cubic function. So what we're able to, so this is degree 3. And the maximum number of turning points is 2. The maximum number of zeros I could have is 1, 2, well, is going to be 3. Allow me to draw another cubic function. We have to, now this is a more elegant cubic function. There we have it. Now, how many turning points does this blue one have? I don't know. It depends what your definition of turning point. I'm going to argue 1. So it doesn't have to have 2 turning points, but it has a maximum number of 2 turning points. So could I draw a cubic? Well, here, do you see how this has overall? It has the left hand and right hand side behavior, right? If you remember that note or that vocabulary from last year, what we see is that my function will have an overall positive slope. Is that true for all cubic functions? No. It's only true for cubic functions in which, I want to see if you can guess, the leading coefficient is positive. All odd functions will behave alike. So sort of like the green one here, my leading coefficient was positive. Overall, I had a positive slope. And the cubic one is also odd. Overall, I'll have a positive slope because my leading coefficient is positive. Now we just did transformations. So I could, there's another cubic function, right? Now, what would the leading coefficient of this cubic function be? Just for fun, it has to be negative because overall the left-hand side has a negative slope about it. The right-hand side has a negative slope about it. All right. I think we're having fun. I'm having fun anyways. So anyways, quartic function, what might it look like? It might go like boom, boom, boom. There's one. This is degree 4. 1, 2, 3 turning points. The maximum number of zeros is 1, 2, 3, 4. But let us not forget that these things can take on devilish looks. So a quartic function could also look like this. If you want to talk about, I heard somebody in the crowd ask, well, what would be the difference between the two? That's what the unit's really about. But do you see how the green is overall upward opening? That would mean that, very similar to a quadratic, any upward opening parabola, the leading coefficient would have to be positive. This red parabola, what do you know about the leading coefficient? It's negative. So this one too would also be negative. All right, perhaps I'm getting ahead of myself. Quintic, let's just do this one for fun. 1, 2, 3, 4, up. There it is. It would be a quintic function, degree 5. It can take quite a nasty look on it. Now, a quintic function could also look like this. It can also behave like a cubic function. What do I want you to take away from all of this? So maximum number of turning points is 4. The highest number of zeros is also 4. I know we could have 1. Really, I would like you to take away from this, if my degree is n, the maximum number of turning points is n minus 1. The maximum number of zeros is n. So really, I hope that we worked on this. I've introduced the idea, if the function's even, the left-hand and right-hand side behavior will mimic those of all even degree functions. Alluded to that, we haven't really discussed it. If a function is an odd degree, the left-hand and right-hand side behavior will mimic those of odd degree functions. Are you a master of odd degree functions? Sure you are, linear functions. So really, what we're going to, polynomials, a lot of the thinking is done through analogy and making comparisons. I hope this is a good start. I understand that the learning is vague so far, but let's continue and see where it takes us.